Webb just revealed something massive: galaxies forming far too early and too small. The evidence shows they shouldn't even exist according to our current understanding. We thought we had a handle on the early universe. We thought we knew how galaxies evolved. The data reveals something far more unsettling. Consider this. Every simulation we've run predicts something different. These infant galaxies are too bright, too compact. The accepted models? They're crumbling before our eyes. Is it possible that our entire framework for understanding the cosmos needs a fundamental rewrite? 600 galaxies, all breaking the rules. And a disturbing pattern is emerging from the James Webb data. It points towards something pretty brutal happening in the early universe. Cosmic cannibalism on a scale we never imagined. Galaxies, as we understood them, were supposed to grow gradually. Small clumps of matter slowly coalescing, gently merging, patiently building up over billions of years. The Webb data suggests something far more violent, something far more efficient. Imagine a bunch of infant galaxies, barely formed, suddenly getting devoured by their larger neighbors. A galactic feeding frenzy, a cosmic dark age buffet. Consider the sheer number of these two early galaxies Webb has spotted. They're not outliers, they're not rare exceptions. They're everywhere, and their existence poses a fundamental challenge to the hierarchical model of galaxy formation, the idea that small things merge to make big things. If these galaxies were formed too quickly, then the accepted models are simply wrong. Something else must have been at play. The leading theory? Rapid accretion through mergers. Basically, these infant galaxies were getting ripped apart and absorbed by larger, more dominant galaxies at an accelerated rate. It's like a high-speed chase where the small guys never stood a chance. The problem is, this level of cosmic cannibalism requires specific conditions. You need a high density of galaxies in a relatively small space. You need gravitational interactions strong enough to tear these galaxies apart. And you need it all to happen incredibly fast. Scientists discovered that the early universe might have been a much more crowded and chaotic place than we previously thought. The galaxies were packed together far more densely than they are today. This created a perfect storm for galactic mergers, a sort of cosmic mosh pit where the weaker galaxies got swallowed whole. The implications extend beyond just galaxy formation. It also affects our understanding of the supermassive black holes that lurk at the center of most galaxies. These black holes are thought to grow in tandem with their host galaxies, feeding on the gas and dust that swirls around them. If galaxies were merging at a higher rate in the early universe, then these black holes would have had access to a much richer food supply. They could have grown to enormous sizes, much faster than predicted. This means the supermassive black holes we see today might have a very different origin story than we thought. Instead of slowly accreting matter over billions of years, they might have experienced a period of rapid growth fueled by the cannibalization of smaller galaxies. And then there's the question of dark matter. Dark matter is the invisible substance that makes up the bulk of the mass in the universe. It plays a crucial role in galaxy formation, providing the gravitational scaffolding that holds galaxies together. If galaxies were merging at a higher rate in the early universe, it could have affected the distribution of dark matter. The gravitational interactions between merging galaxies could have stirred up the dark matter, creating a more complex and lumpy distribution than predicted by current models. The analysis continued. The early universe was a violent place, a battlefield where galaxies fought for survival, and the winners got to feast on the losers. Further examination revealed a second, equally disturbing consequence of this cosmic cannibalism. It could have stunted the growth of many galaxies. If a galaxy gets swallowed whole before it has a chance to fully form, it never reaches its full potential. It becomes a mere building block in a larger structure, forever deprived of its own independent existence. This could explain why we see so many dwarf galaxies in the universe today. These small, faint galaxies might be the remnants of galaxies that were cannibalized in the early universe. They are the cosmic leftovers, the scraps that were left behind after the big galaxies had their fill. Measurements showed the early universe was a zero-sum game. For every galaxy that grew to become a giant, dozens of others were sacrificed. The process was brutal, but it was also incredibly efficient. It allowed the universe to rapidly build up the large-scale structures we see today. But here's what's wild. What if this cannibalism isn't just a thing of the ancient past? What if it's still happening today? There's growing evidence that even in the present-day universe, galaxies are still merging and cannibalizing each other. Our own Milky Way galaxy, for example, is currently in the process of devouring several smaller galaxies. The Sagittarius dwarf galaxy is being ripped apart by the Milky Way's gravity, its stars and gas being slowly incorporated into our own galaxy. So, cosmic cannibalism isn't just a relic of the early universe. It's an ongoing process that continues to shape the evolution of galaxies today. It's a reminder that the universe is a dynamic and ever-changing place, where galaxies are constantly interacting, merging, and sometimes devouring each other. The James Webb Telescope is offering a disturbing glimpse into the violent past, and possibly the violent present, of our cosmic neighborhood. Ever wonder if galaxies actually grow up at the same speed? Like, do some hit their growth spurt way earlier than others? The James Webb Telescope is starting to suggest the answer is a resounding yes. What we're seeing in some of these early galaxies is accelerated development. Galaxies that are far more mature than their age would suggest. They're packing on stellar mass at rates that seem impossible given the time they've had to form. It's like finding a teenager who's already 6'10" and built like a linebacker. You'd have to wonder what kind of growth hormones they're on, right? In this case, the growth hormones are likely galactic mergers, ancient collisions that fueled rapid star formation and accelerated the aging process. Now, think about this for a second. If galaxies are growing at different rates, then our whole picture of the early universe gets a lot more complicated. We can't just assume that all galaxies at a certain redshift are at the same stage of development. Some might be precocious youngsters, while others are lagging behind. This has huge implications for how we interpret the data from the James Webb Telescope. If we don't account for this accelerated growth, we might be miscalculating the ages and distances of these early galaxies. We might be underestimating their masses. We might be completely misunderstanding their place in the cosmic timeline. Further examination revealed something even more unsettling. It wasn't just that some galaxies were growing faster, it was that these accelerated growth spurts seemed to be linked to periods of intense galactic cannibalism. The galaxies that were growing the fastest were also the ones that had experienced the most mergers and collisions. Consider this. A galaxy gobbles up a smaller galaxy. All that extra gas and dust gets compressed, triggering a massive burst of star formation. The galaxy suddenly becomes much brighter and more massive. It ages prematurely, skipping ahead in its evolutionary timeline. It's a cosmic shortcut, a way for galaxies to cheat their way to maturity. But it comes at a cost. These cannibalistic galaxies often become distorted and irregular in shape. They develop messy, chaotic structures that betray their violent past. This means that the most massive galaxies we see today might not be the ones that formed in the most pristine conditions. They might be the survivors of countless cosmic battles, the victors who emerged from the galactic arena with the spoils of war. And what about the losers? What happened to the galaxies that were swallowed whole? Well, some of them might have been completely destroyed, their stars and gas scattered into the intergalactic medium. Others might have survived as faint, diffuse tidal streams, orbiting around the larger galaxy like ghostly remnants of a forgotten past. These tidal streams are incredibly difficult to detect, but the James Webb Telescope is starting to reveal them in unprecedented detail. We're seeing faint wisps of light stretching out from galaxies like the tattered remains of a cosmic tapestry. The implications extend beyond just understanding the growth of individual galaxies. It also affects our understanding of the large-scale structure of the universe. If galaxies are constantly merging and cannibalizing each other, then the distribution of galaxies in the universe is not just determined by gravity, it's also shaped by these violent interactions. This could explain why we see so many galaxy clusters, massive collections of galaxies bound together by gravity. These clusters might have formed through a process of hierarchical merging, where smaller groups of galaxies gradually coalesce into larger structures. The data reveals that the early universe was a much more dynamic and chaotic place than we previously thought. It was a cosmic demolition derby where galaxies were constantly crashing into each other, merging together, and tearing each other apart. Scientists discovered that the James Webb Telescope is giving us a front-row seat to this ongoing spectacle. We're seeing the universe in all its messy, violent glory, and it's forcing us to rethink everything we thought we knew about galaxy formation and evolution. So, the next time you look up at the night sky, remember that the seemingly peaceful galaxies you see are the products of billions of years of cosmic violence. They are the survivors of countless battles, the winners and losers of an epic struggle for survival. And the James Webb Telescope is helping us to unravel the secrets of this cosmic drama, one galaxy at a time. It's not just about beautiful images, it's about understanding the fundamental processes that have shaped the universe we live in. The analysis continued, pushing the limits of what we thought was possible. The question became how much of what we think we know about the early universe is simply wrong. This kept me up last night, honestly. The implications of what Webb is finding regarding dark matter, it's unsettling. For decades, we've treated dark matter as this background player, a scaffolding that galaxies form within, a silent partner in the cosmic dance. But what if it's not so silent? What if it's actively shaping galactic evolution in ways we never imagined? Consider the simulations. For years, they've struggled to accurately reproduce the diversity of galaxies we see in the universe. They either produce too many dwarf galaxies, or the spiral arms are too tightly wound, or the central bulges are too prominent. There's always something that doesn't quite match reality. One of the main assumptions in these simulations is that dark matter interacts with ordinary matter, primarily through gravity. It pulls on galaxies, providing the extra mass needed to hold them together. But that's about it. It's a very hands-off relationship. But what if dark matter can interact with ordinary matter through other, weaker forces? What if it can subtly influence the way gas clouds collapse, or the way stars form, or the way galaxies merge? The James Webb Telescope is giving us hints that this might be the case. It's observing the distribution of dark matter in the early universe with unprecedented precision. And what it's finding is unexpected. The data reveals that dark matter isn't as smoothly distributed as we thought. Instead, it's clumpy, forming dense knots and filaments that can significantly affect the evolution of nearby galaxies. These dark matter clumps can act like cosmic wrecking balls, disrupting the delicate structure of galaxies as they pass through. They can trigger bursts of star formation in some regions, while suppressing it in others. They can even tear galaxies apart, stripping away their outer layers of stars and gas. And here's where it gets really unsettling. The simulations that take these dark matter interactions into account are starting to produce galaxies that look much more like the real thing. The dwarf galaxies are the right size and number. The spiral arms are the right shape. The central bulges are the right prominence. It's as if by tweaking the properties of dark matter, we can finally unlock the secrets of galaxy formation. This suggests that dark matter plays a much more active and dynamic role in the universe than we previously thought. It's not just a passive scaffolding, it's an active sculptor, shaping the destinies of galaxies through subtle but powerful interactions. Scientists discovered that the early universe's galaxies, awash in greater concentrations of dark matter, were more affected than the galaxies we see today. This would explain the vast differences in galactic structure between then and now. The implications extend beyond just understanding galaxy formation. It also affects our understanding of dark matter itself. If dark matter can interact with ordinary matter through forces other than gravity, then it opens up a whole new realm of possibilities for what dark matter could be. It could be made up of particles that we haven't even discovered yet, particles that interact with each other and with ordinary matter in ways that we don't yet understand. This would mean the current models are fundamentally incomplete. The equations we've used for decades are missing key terms. The assumptions we've made about the nature of dark matter are wrong. Here's what's wild. Consider that the vast majority of matter in the universe is dark matter. If it turns out to be more complex and interactive than we thought, then it could rewrite our entire understanding of cosmology. It could explain some of the biggest mysteries in the universe, such as the nature of dark energy, the accelerating expansion of the universe, and the origin of the cosmic microwave background. It's a terrifying prospect, but also an incredibly exciting one. The James Webb Telescope is giving us a glimpse into a hidden world, a world where dark matter reigns supreme. The analysis continued and scientists developed new simulations incorporating these potential interactions. They wanted to see if these models could not only reproduce the galaxies we see, but also predict new phenomena that we could then test with the James Webb Telescope. It's a constant feedback loop, theory informing observation, and observation refining theory. The question became, can we use the James Webb Telescope to definitively prove whether or not dark matter interacts with ordinary matter through forces other than gravity? Can we identify specific signatures of these interactions, such as subtle distortions in the shapes of galaxies or unusual patterns in the distribution of stars and gas? The stakes are incredibly high. If we can prove that dark matter is more interactive than we thought, it would open up a whole new chapter in our understanding of the universe. It would give us new tools to probe the mysteries of dark matter and dark energy, and it could even lead to the discovery of new particles and forces of nature. It's a long shot, but it's a shot worth taking. And the James Webb Telescope is giving us the best chance we've ever had. The implications extend to our understanding of the universe's future. If dark matter interactions play a significant role in galaxy evolution, then the long-term fate of galaxies and the universe itself could be very different from what we currently predict. Galaxies might merge more frequently, or they might be torn apart more easily. The distribution of matter in the universe might become more clumpy and chaotic. It's like we're standing on the edge of a precipice, peering into the unknown. The James Webb Telescope is showing us a universe that is far more complex and dynamic than we ever imagined, and it's forcing us to confront some of the deepest mysteries of existence. What is dark matter? What is dark energy? And what is the ultimate fate of the universe? The answers, it seems, may be far more terrifying and far more awe-inspiring than we ever dared to dream. Scientists discovered that the very fabric of space-time itself might be subtly influenced by these dark matter interactions, creating ripples and distortions that could be detected by future generations of telescopes. The exploration continues. December 2023. Something didn't add up. It wasn't a single data point or one rogue galaxy behaving strangely. It was a persistent, nagging discrepancy that kept appearing across multiple Webb observations. Galaxies, particularly those in the early universe, seemed to be rotating too fast. The expected relationship between a galaxy's visible mass and its rotation speed wasn't holding. We've long understood that galaxies aren't just swirling collections of stars and gas. They're embedded within vast halos of dark matter, which provides the extra gravitational pull needed to hold them together as they spin. Without dark matter, galaxies would simply fly apart. But Webb was showing us galaxies that were spinning even faster than predicted, even when accounting for the expected amount of dark matter. It was as if there was even more missing mass than we thought. This intensified what's known as the missing mass problem. Let's examine this a little closer. The missing mass problem isn't new. For decades, astronomers have known that the visible matter in the universe, the stars, gas, and dust that we can see with our telescopes, accounts for only a small fraction of the total mass needed to explain the observed gravitational effects. Dark matter was introduced as a solution to this problem, providing the extra mass needed to explain galaxy rotation curves and the formation of large-scale structures. So, what does it mean when Webb reveals that the galaxies in the early universe are rotating faster than we can account for, even with dark matter? One possibility is that our understanding of dark matter itself is incomplete. Perhaps dark matter is even more abundant than we thought, or perhaps its distribution within galaxies is different than we currently model, or maybe its properties change over cosmic time. Another possibility is that there's something fundamentally wrong with our understanding of gravity. Modified Newtonian dynamics, or MOND, proposes that the laws of gravity are different on galactic scales than they are in our solar system. MOND has been around for decades, and it's always been on the fringe. These new Webb observations, they're breathing new life into MOND and other alternative theories of gravity. The evidence shows that we might need to rethink some fundamental assumptions about how gravity works on the larger scales. The implications extend beyond just galaxy rotation. The missing mass problem also affects our understanding of galaxy formation and evolution. Simulations of galaxy formation rely on dark matter to provide the gravitational scaffolding needed for galaxies to coalesce from the primordial soup of the early universe. If the amount or distribution of dark matter is different than we thought, then our simulations may be producing inaccurate predictions about the number and types of galaxies we should see. Here's what's wild. These faster-than-expected rotation speeds could also be influenced by the interaction between dark matter and normal matter. It's possible that there's a force beyond gravity that's influencing the movement of stars and gas within these early galaxies. I mean, The missing mass problem could be a sign that our entire picture of the universe needs a major overhaul. Scientists discovered that the discrepancy is most pronounced in the earliest, most distant galaxies observed by Webb. These galaxies are so far away that their light has taken billions of years to reach us, giving us a glimpse into the universe as it existed just a few 100 million years after the Big Bang. This means that whatever is causing the faster than expected rotation speeds was already in place in the very early universe. This puts even tighter constraints on the possible explanations. It also suggests that the processes that shaped the first galaxies were fundamentally different from the processes that shape galaxies today. And then there's the unsettling possibility that we're missing something else entirely, something we haven't even conceived of yet. Some unknown physics that's influencing the behavior of galaxies on the larger scales. The analysis continued. Scientists began to explore a range of exotic possibilities, from axions and sterile neutrinos to entirely new types of dark matter particles. Each possibility came with its own set of challenges and predictions. The data reveals that no single explanation seems to fully account for the Webb observations. The missing mass problem isn't just a puzzle for astronomers, it's a fundamental challenge to our understanding of the universe. It forces us to question some of our most basic assumptions about gravity, dark matter, and the formation of galaxies. It's a reminder that despite all the progress we've made in understanding the cosmos, there are still vast unknowns waiting to be explored. This means we need to be ready for a paradigm shift. The James Webb Telescope is not just confirming what we already know. It's pushing the boundaries of our knowledge and forcing us to confront the limitations of our current theories. It's a call to arms for a new generation of scientists to develop new models and new experiments to unravel the mysteries of the missing mass problem. The implications extend to our understanding of the universe's ultimate fate. If dark matter is more complex than we thought, or if gravity behaves differently on large scales, then our predictions about the future of the universe could be wildly inaccurate. Meanwhile, the search for answers continues. Astronomers are using Webb to observe more and more distant galaxies, hoping to find clues that will shed light on the missing mass problem. They're also developing new computer simulations and theoretical models to explore different possibilities. The unsettling truth is that we may be on the verge of discovering something truly profound about the nature of the universe, something that will challenge our most deeply held beliefs and reshape our understanding of reality. The exploration continues. We thought we had the universe figured out. We were wrong. For decades, the lambda-CDM model has been the cornerstone of cosmology. It's the framework that describes the evolution of the universe, from the Big Bang to the present day. It incorporates dark matter, dark energy, and the standard model of particle physics. It's elegant, it's comprehensive, and it's been incredibly successful at explaining a wide range of observations. But now, the James Webb Telescope is throwing a wrench into the works. The lambda-CDM model predicts a certain distribution of matter in the universe, with galaxies forming in a hierarchical manner. Small galaxies merge to form larger galaxies, and these larger galaxies eventually cluster together to form the cosmic web. The model also predicts the number and properties of galaxies at different redshifts, corresponding to different epochs in the universe's history. Webb is seeing something else entirely. The telescope is revealing an abundance of massive, fully formed galaxies at redshifts that are simply too high, meaning they existed far too early in the universe's history. These galaxies are far more massive and mature than the lambda-CDM model predicts. They shouldn't be there, at least not in such numbers. This discrepancy is a major challenge to the lambda-CDM model. It suggests that our understanding of galaxy formation is incomplete, or even fundamentally flawed. It raises the possibility that there are other factors at play that we haven't yet considered. What could these factors be? One possibility is that the properties of dark matter are different than we thought. Perhaps dark matter interacts with itself or with ordinary matter in ways that we don't yet understand. This could lead to a different pattern of structure formation, with galaxies forming more rapidly and efficiently in the early universe. Another possibility is that our understanding of gravity is incomplete. General relativity, Einstein's theory of gravity, has been incredibly successful at explaining a wide range of phenomena, but it's possible that general relativity breaks down on the largest scales or in the very early universe. This could lead to a different expansion history of the universe and a different pattern of structure formation. Or perhaps something even more exotic is going on. Maybe there are new particles or new forces that we haven't yet discovered. Maybe the universe is more complex and mysterious than we ever imagined. The implications of these findings are profound. If the lambda CDM model is wrong, then we need to rethink our entire understanding of the universe. We need to develop new models and new theories that can explain the Webb observations. This is a daunting task, but it's also an incredibly exciting one. It's a chance to push the boundaries of our knowledge and to uncover new truths about the cosmos. The scientific community is now grappling with this challenge. Astronomers and physicists are working together to develop new models and new experiments that can test the lambda CDM model and explore alternative possibilities. They're using Webb to observe more and more distant galaxies, hoping to find clues that will shed light on the missing pieces of the puzzle. They're also developing new computer simulations and theoretical models to explore different possibilities. Consider this: the Webb data isn't just a minor tweak to our existing models. It's potentially a sign that something fundamental is missing from our understanding. It's like discovering a new continent on Earth. It forces us to redraw the map and rethink our entire understanding of geography. The challenge lies in reconciling these new observations with the vast body of evidence that supports the lambda CDM model. The model has been incredibly successful at explaining a wide range of phenomena, from the cosmic microwave background to the large-scale distribution of galaxies. It's not easy to simply discard a model that has been so successful for so long, but the Webb data is undeniable. It's a clear sign that something is amiss. It's a call to arms for a new generation of scientists to develop new models and new experiments that can unravel the mysteries of the early universe. The discomfort is palpable in the scientific community. For decades, lambda CDM has been the story. Now, the story is changing. The analysis continued, with scientists focusing on the most distant galaxies Webb could detect. The goal? To find more. Examples that either confirmed or refuted the current models. And then, there's a problem with the Webb data that nobody seems to be talking about. It's not just that the early galaxies are too bright or too massive. It's that they're too evolved. We're seeing fully formed spiral galaxies with well-defined structures far earlier in the universe than our current models predict. Think about that for a second. According to lambda CDM, these galaxies should still be in the process of forming. They should be messy, chaotic collections of gas and dust, slowly coalescing into larger structures. Instead, we're seeing galaxies that look like they've been around for billions of years. How can this be? One possibility is that our understanding of galaxy formation is incomplete. We may be missing some key ingredients or processes that accelerate the formation of galaxies in the early universe. Perhaps dark matter halos formed much faster than we thought, providing a gravitational scaffold for galaxies to assemble more quickly. Or maybe there were more frequent and intense mergers between smaller galaxies, leading to the rapid growth of larger galaxies. Another possibility is that our understanding of the early universe itself is flawed. The lambda CDM model assumes that the universe began in a hot, dense state and has been expanding and cooling ever since. But what if the early universe was different than we thought? What if there were periods of accelerated expansion or contraction that affected the formation of galaxies? These are not easy questions to answer. The early universe is a difficult place to study. It's so far away that the light from these objects has been stretched and redshifted, making it difficult to observe them in detail. And the early universe was a very different place than the universe we see today. It was hotter, denser, and more chaotic. The Webb telescope is giving us a glimpse into this mysterious epoch, but it's also raising more questions than answers. We're seeing things that we simply can't explain with our current models. It's like trying to assemble a puzzle with half the pieces missing. We can see the overall picture, but we can't quite make sense of all the details. We need more data, more observations, and more theoretical work to fill in the gaps. The scientific community is now grappling with these challenges. Astronomers are using Webb to observe more and more distant galaxies, hoping to find clues that will shed light on the missing pieces of the puzzle. They're also developing new computer simulations and theoretical models to explore different possibilities. Consider the implications if these early galaxies formed far faster than our models allow. This suggests that the conditions in the early universe were significantly different than we currently believe. It would potentially require us to revise our understanding of dark matter, dark energy, and the fundamental laws of physics that govern the cosmos. The Webb data is not just a minor correction to our existing models, it's a potential sign that something fundamental is missing from our understanding of the universe. It's a daunting but ultimately exhilarating prospect. It's an opportunity to rewrite the textbooks and to uncover new truths about the cosmos. The problem extends beyond just the speed of galaxy formation. It also concerns the chemical composition of these early galaxies. The models predict that early galaxies should be relatively pristine, composed mostly of hydrogen and helium, with only trace amounts of heavier elements. However, Webb has detected surprisingly high levels of heavy elements in some of these galaxies. These heavy elements, such as carbon, oxygen, and iron, are forged in the cores of stars and released into the universe through supernovae explosions. The presence of these elements in early galaxies suggests that star formation must have been much more rapid and efficient than we thought. It also raises questions about the origin of these elements. Where did they come from? How did they get into these galaxies so quickly? This also means we may need to rethink our understanding of the first stars. These population 3 stars are theorized to be incredibly massive and short-lived, exploding as supernovae and seeding the universe with heavy elements. But the abundance of heavy elements that Webb is seeing suggests that these stars may have been even more massive and more numerous than we thought. Or perhaps there was another source of heavy elements that we haven't yet considered. The early universe is turning out to be a much more complex and dynamic place than we ever imagined. The Webb telescope is revealing a whole new layer of mysteries, and it's forcing us to rethink our fundamental assumptions about the cosmos. And then we get to the supermassive black holes. Webb just revealed something massive. Not just a refinement of existing theories, but something that challenges the very foundation of how we thought galaxies formed in the early universe. We're talking about the established models of hierarchical galaxy formation, the ones that have been the bedrock of cosmological understanding for decades. These models predict that small galaxies should merge over time, gradually building up into larger galaxies like our own Milky Way. It's a bottom-up approach, a cosmic construction project spanning billions of years. But Webb is throwing a wrench into that whole picture. The telescope is seeing fully formed massive galaxies appearing far too early in the universe's history, within the first billion years after the Big Bang. These galaxies are far larger and more mature than anything the models predicted could exist at that time. It's like finding fully grown trees in a place where only saplings should be. The problem isn't just that these galaxies are large, it's that they're abundant. Webb is finding them all over the place. This suggests that the early universe was far more efficient at forming large galaxies than we ever thought possible. It challenges the idea that galaxy formation was a slow, gradual process. This is a problem because the hierarchical model is closely tied to our understanding of dark matter. Dark matter is the invisible substance that makes up the majority of the universe's mass, and it's thought to play a crucial role in galaxy formation. The models predict that dark matter halos, vast concentrations of dark matter, provide the gravitational scaffolding upon which galaxies are built. Smaller halos merge to form larger halos, and galaxies form within these halos. But the abundance of massive galaxies in the early universe suggests that dark matter halos must have formed much more quickly and efficiently than the models predict. It's possible that our understanding of dark matter itself is incomplete. Perhaps dark matter particles interact with each other in ways we don't yet understand, or perhaps there are other forces at play that we haven't yet accounted for. The implications extend beyond just galaxy formation. If our understanding of galaxy formation is wrong, it could also affect our understanding of the large-scale structure of the universe. The distribution of galaxies in the universe is thought to be determined by the distribution of dark matter. So if our understanding of dark matter is incomplete, it could mean that our understanding of the universe's structure is also flawed. Here's what's wild. These early galaxies aren't just massive, they're also incredibly dense. They're packed with stars, and they're forming new stars at an astonishing rate. This suggests that the early universe was a much more violent and chaotic place than we ever imagined. The conventional wisdom held that the early universe was a relatively calm and orderly place, with galaxies forming slowly and gradually. But Webb is showing us that it was a cosmic cauldron, a maelstrom of star formation and galactic mergers. It's like the universe was in a hurry to build these galaxies, and it was using every trick in the book to get the job done. This raises a fundamental question. What was driving this rapid galaxy formation? What were the conditions in the early universe that allowed these galaxies to form so quickly and efficiently? There are several possible explanations. One possibility is that the early universe was filled with more gas than we thought. Gas is the raw material for star formation, so if there was more gas available, galaxies could have formed more quickly. Another possibility is that the early universe was more efficient at converting gas into stars. Star formation is a complex process that depends on a variety of factors, including the density of the gas, the temperature of the gas, and the presence of heavy elements. If the conditions in the early universe were just right, galaxies could have formed stars at a much faster rate. Scientists discovered that the early universe may have had different laws of physics. It's a radical idea, but it's one that's being taken seriously by some cosmologists. If the laws of physics were different in the early universe, it could have allowed galaxies to form in ways that are impossible today. It's a difficult concept to wrap your head around, but it's important to remember that our understanding of the universe is constantly evolving. What we think is true today may be proven wrong tomorrow. The Webb telescope is helping us to push the boundaries of our knowledge and to explore the mysteries of the cosmos. And this particular mystery is one of the biggest. How did galaxies form so quickly in the early universe? And then we get to the question of dark matter's role. Is it possible that we've overestimated its importance? If we've overestimated the role of dark matter, the implications are staggering. Our current understanding of galaxy formation relies heavily on dark matter's gravitational influence to pull together the initial seeds of galaxies. Without it, the process becomes significantly more challenging to explain, especially on the timescale that Webb is revealing. Consider this. What if the universe isn't quite as dark matter-dominated as we thought? What if other factors, currently underestimated, are playing a more significant role? Perhaps there's a missing ingredient in our models, something we haven't yet accounted for that significantly alters the dynamics of early galaxy formation. These possibilities lead to some unsettling questions about our fundamental understanding of cosmology. Are our simulations accurately reflecting the conditions of the early universe? Are we correctly interpreting the data we're receiving from Webb? If the rapid formation of these galaxies cannot be explained by our current models, it suggests a deeper problem with our understanding of the underlying physics. One potential answer lies in the nature of dark matter itself. We assume it interacts gravitationally, but what if it has other, more complex interactions that we're not yet aware of? Could these interactions have been more prominent in the early universe, influencing galaxy formation in ways that are no longer observable today? It's also possible that we're misinterpreting the data from Webb. The light from these distant galaxies has traveled for billions of years, and it's been affected by the expansion of the universe and the intervening matter. Are we correctly accounting for these effects? Could there be systematic errors in our measurements that are skewing our understanding of the galaxy's properties? Or it could be something even more fundamental. The standard model of cosmology, while incredibly successful in explaining many aspects of the universe, has its limitations. It doesn't account for dark energy, for example, and it struggles to explain the observed distribution of matter on the largest scales. Perhaps the rapid galaxy formation observed by Webb is a sign that the standard model needs a major overhaul. The analysis continued. Scientists began to explore alternative theories of gravity, ones that modify Einstein's theory of general relativity to account for the accelerated expansion of the universe and the behavior of dark matter. These theories, while still in their infancy, offer a potential way to explain the rapid formation of galaxies without relying so heavily on dark matter. Modified Newtonian dynamics, or MOND, is one such theory. It suggests that at very low accelerations, gravity behaves differently than predicted by Newton's law. This could have significant implications for the formation of galaxies, allowing them to form more quickly and efficiently than predicted by standard models. Another possibility is that the early universe was simply more chaotic than we thought. Perhaps there were regions of space that were significantly denser than average, allowing galaxies to form more quickly in those regions. These dense regions could have been seeded by quantum fluctuations in the very early universe, or by some other unknown process. Whatever the explanation, it's clear that the Webb telescope is challenging our fundamental assumptions about galaxy formation. It's forcing us to reconsider our models and to explore new ideas. It's a reminder that our understanding of the universe is constantly evolving and that there's still much that we don't know. This means every simulation needs rewriting. Every assumption needs re-examining. The textbooks, in some sense, might be obsolete. We're not just tweaking the existing models, we're potentially looking at a paradigm shift in how we understand the cosmos. The rate at which these galaxies appeared suggests an energy and organization in their early universe that defies easy explanation. Measurements showed a surprising abundance of heavy elements in these early galaxies. Heavy elements are formed in the cores of stars and released into the universe through supernova explosions. The presence of these elements suggests that these galaxies went through a period of intense star formation very early in their history. But how did they form so many stars so quickly? It's a chicken and egg problem. You need stars to create heavy elements, but you also need heavy elements to cool the gas clouds that form stars. So how did these early galaxies get enough heavy elements to kickstart the process of star formation? This is one of the biggest mysteries facing astronomers today. The Webb telescope is providing us with a wealth of new data, but it's also raising new questions. It's a reminder that the universe is a complex and mysterious place, and that we still have much to learn. And as we learn, everything we thought we knew might be wrong. It's unnerving, but also exhilarating. The universe is far stranger and far more energetic than we ever imagined. And then we're faced with the question of supermassive black holes. Did they form before the galaxies, or did the galaxies form around them? You've been told that galaxies are solitary islands in space. That's not quite right. Consider this. Galaxies, especially in the early universe, weren't just sitting pretty, minding their own business. They were locked in a gravitational dance, a cosmic ballet of attraction and destruction. And the Webb telescope is giving us a front-row seat to some of the most extreme choreography imaginable. These early galaxies, packed much closer together than galaxies today, were constantly interacting. Imagine a crowded dance floor where everyone's bumping into each other. Except instead of awkward apologies, these galactic collisions resulted in bursts of star formation and the merging of supermassive black holes. The evidence shows that these interactions were far more common and far more violent than we previously thought. Webb's infrared vision pierces through the dust and gas that obscures these events in visible light, revealing the chaotic processes at play. We're seeing galaxies ripped apart, their stars scattered across intergalactic space, and their supermassive black holes spiraling towards a cataclysmic merger. And this is where the terrifying part comes in. These mergers weren't gentle affairs. They were titanic collisions that unleashed unimaginable amounts of energy. As galaxies collided, their supermassive black holes would eventually find each other, drawn together by gravity. They'd then begin a slow, agonizing dance, circling each other for millions of years, gradually getting closer and closer. As they spiraled inward, they'd stir up the surrounding gas and dust, creating a swirling disk of superheated material. This disk, known as an accretion disk, would become incredibly bright, emitting vast amounts of radiation across the electromagnetic spectrum. It's like a cosmic blender pulverizing matter and spitting out energy. Scientists discovered that this process would continue until the black holes finally collided, merging into a single, even more massive black hole. This merger would unleash a final burst of gravitational waves, ripples in the fabric of space-time that would propagate across the universe. The implications extend far beyond just the merger of black holes. These galactic collisions played a crucial role in shaping the evolution of galaxies themselves. They triggered bursts of star formation, fueled the growth of supermassive black holes, and redistributed heavy elements throughout the universe. It's a messy, violent, and utterly fascinating process. And the Webb telescope is allowing us to witness it in unprecedented detail. We're seeing the universe in its infancy, a time of rapid change and intense activity. It's a stark reminder that the cosmos is not a static, unchanging place. It's a dynamic, evolving system, constantly reshaped by the forces of gravity and energy. Here's what's wild. The frequency of these early mergers suggests that supermassive black holes may have actually seeded the growth of the earliest galaxies. Did the black hole come first, or the galaxy? It's a question that Webb is uniquely positioned to answer. Imagine two galaxies, each containing billions of stars and a supermassive black hole at its center. As they collide, their stars are flung around like marbles in a pinball machine. The gas and dust are compressed and heated, triggering a frenzy of star formation. And the two black holes, locked in a deadly embrace, begin their final dance. This dance is not silent. It generates gravitational waves, ripples in space-time that propagate outwards at the speed of light. These waves are incredibly faint, but they carry with them information about the mass and spin of the black holes, as well as the details of their merger. Webb can't directly detect gravitational waves, but it can see the after-effects of these mergers. It can observe the intense radiation emitted by the accretion disks, as well as the changes in the shape and structure of the galaxies themselves. By studying these mergers in detail, astronomers hope to understand how supermassive black holes grew to such enormous sizes so quickly. They also hope to learn more about the role that mergers played in the formation of galaxies and the distribution of heavy elements. The data reveals that the early universe was a much more chaotic and violent place than we previously thought. Galaxies were constantly colliding and merging, and supermassive black holes were growing at an astonishing rate. It was a time of intense activity and rapid change. Meanwhile, the Webb telescope is continuing to collect data on these early galaxies, providing us with a wealth of new information about the formation and evolution of the universe. It's a journey of discovery that is just beginning, and it promises to revolutionize our understanding of the cosmos. And then there's the question of what happens after the merger. Does the resulting galaxy settle down into a stable configuration? Or does it continue to evolve and interact with other galaxies? Does the merged black hole continue to grow, or does it eventually run out of fuel? The Big Bang wasn't quiet. We tend to picture it as a single explosive event, but the Webb telescope is showing us it was more like a continuous barrage of smaller explosions, echoes of the initial fury still reverberating across the cosmos. These echoes aren't literal sound waves, of course. They're the traces left behind by the incredible energy released in the early universe. This energy heated up the surrounding gas, ionized atoms, and triggered a cascade of reactions that shaped the first galaxies. Consider the quasars. These are supermassive black holes that are actively feeding on gas and dust. They're incredibly bright, and they can be seen from billions of light-years away. Webb is allowing us to study quasars in the early universe with unprecedented detail. What's being discovered? The data reveals that these quasars were much more common and much more powerful than we previously thought. Think about it. These quasars are like beacons, shining a light on the gas and dust that surrounds them. By studying the light that passes through this gas, astronomers can learn about its composition, temperature, and density. It's like using a cosmic flashlight to illuminate the hidden corners of the early universe. Scientists discovered that the gas surrounding these early quasars is much hotter and more turbulent than expected. This suggests that it was being heated by something other than the quasar's radiation. The most likely explanation is that it was being heated by the shocks and turbulence created by the constant mergers of galaxies. The implications extend beyond just the temperature of the gas. The composition is unexpected too. Webb is detecting elements like carbon, oxygen, and nitrogen in these early galaxies, elements that shouldn't have been present in such abundance so early in the universe. Where did these elements come from? They were forged in the hearts of stars. But the first stars were massive and short-lived. They exploded as supernovae, scattering these heavy elements into the surrounding gas. It turns out that the process of enriching the universe with these elements was far faster and more efficient than scientists had modeled. And then there's the dark matter. We know that dark matter makes up the bulk of the mass in the universe, but we don't know what it is. Webb's observations of the early universe are providing us with new clues about the nature of dark matter. The analysis continued. By studying the way that dark matter clumps together, scientists can learn about its properties. The data suggests that dark matter may have played a more active role in the formation of the first galaxies than we previously thought. Here's what's wild. It's not just the individual galaxies that are affected by these echoes of the Big Bang. It's the entire large-scale structure of the universe. Webb is mapping the distribution of galaxies across vast distances, revealing a network of filaments and voids that stretches across the cosmos. These filaments are like cosmic highways, guiding galaxies towards regions of higher density. The voids are like empty bubbles, where there are very few galaxies. The structure is thought to have been seeded by tiny fluctuations in the density of the early universe, fluctuations that were amplified by the force of gravity. The echoes of the Big Bang are still shaping the large-scale structure of the universe. Measurements showed that the filaments are denser and more tightly packed than predicted. This suggests that the force of gravity was stronger in the early universe, or that there was more dark matter than we thought. Further examination revealed a new population of faint, dwarf galaxies that are lurking in the voids. These galaxies are too faint to be seen by other telescopes, but Webb's infrared vision is able to pick them out. The existence of these dwarf galaxies challenges our understanding of galaxy formation. Why did these galaxies form in the voids where there is so little matter? It's a puzzle, and the universe is filled with them. These faint galaxies are incredibly old and pristine, offering a glimpse into the earlier stages of galaxy formation. They are like living fossils, preserving a record of the conditions that existed in the early universe. This means that the early universe was not a uniform and homogeneous place. It was a complex and dynamic environment, filled with surprises and mysteries. The Webb telescope is just beginning to scratch the surface of what's out there. It's a journey of discovery that will continue for many years to come. The implications extend. The early universe was a crucible where the building blocks of galaxies were forged. It was a time of intense activity and rapid change. The Webb telescope is providing us with a front-row seat to this cosmic drama. What happens next? As Webb continues to collect data, we can expect to learn even more about the echoes of the Big Bang. We can expect to discover new galaxies, new quasars, and new phenomena that will challenge our understanding of the universe. The universe has a story to tell, and Webb is helping us listen. 5%. That's how much of the universe we can actually see. The rest? Dark matter, dark energy, and a whole lot of questions. And the James Webb Telescope is throwing gasoline on those questions. Future observations are paramount. This isn't a one-and-done situation. We're talking about a continuous process of data collection, analysis, and theoretical refinement. Webb's capabilities are so far beyond anything we've had before that every new observation has the potential to rewrite textbooks. Consider, for instance, the planned Deep Field surveys. These are long-exposure images of seemingly empty patches of sky, designed to capture the faintest, most distant objects. These surveys promise to reveal even more about the early universe, potentially pushing back the boundaries of what we think we know about galaxy formation and evolution. The telescope's spectroscopic capabilities will also play a crucial role. Spectroscopy allows astronomers to analyze the light emitted by objects, breaking it down into its constituent colors. This provides a wealth of information about the object's composition, temperature, density, and velocity. By studying the spectra of distant galaxies, astronomers can learn about the conditions that existed in the early universe and how these conditions shaped the galaxies we see today. Moreover, Webb's infrared vision is uniquely suited to studying the formation of stars and planets. Infrared light can penetrate the dense clouds of gas and dust that obscure these processes from optical telescopes. This means that Webb can provide unprecedented views of star-forming regions, allowing astronomers to study the birth of stars and planets in detail. The data reveals new insights into the processes that led to the formation of our own solar system. But it's not just about looking farther and seeing fainter, it's also about looking at things in new ways. Webb's data is forcing astronomers to rethink some of their most fundamental assumptions about the universe. Here's what's wild. We're not just filling in the blanks in our existing models. We're discovering that some of the models themselves are fundamentally flawed. The unexpectedly bright and massive galaxies observed by Webb in the early universe are a prime example. These galaxies simply shouldn't exist according to our current understanding of galaxy formation. They're too big, too bright, and they formed too quickly. This raises a number of profound questions. What processes allowed these galaxies to form so rapidly? Was the early universe fundamentally different from what we thought? Are there new physics at play that we don't yet understand? The search for answers will require a multi-pronged approach. Astronomers will need to combine Webb's observations with data from other telescopes, both on the ground and in space. They'll also need to develop new theoretical models that can explain the observed phenomena. And then there's the question of dark matter. We know that dark matter makes up the vast majority of the matter in the universe, but we still don't know what it is. Webb's observations may provide new clues about the nature of dark matter. By studying the distribution of dark matter in galaxies and galaxy clusters, astronomers can test different theories about its properties. The implications extend beyond just our understanding of the early universe. They touch on some of the most fundamental questions in science. What is the nature of gravity? What are the fundamental particles that make up the universe? What is the ultimate fate of the cosmos? Webb isn't just a telescope, it's a time machine, it's a window into the past. It's a tool that is allowing us to explore the universe in ways we never thought possible. And as Webb continues to collect data, we can expect to be surprised, challenged, and ultimately enlightened. The universe is full of mysteries, and Webb is helping us to unravel them, one observation at a time. It's a journey of discovery that will continue for many years to come. The analysis continued. Scientists discovered even more faint galaxies lurking in the shadows of larger galaxies. These faint galaxies are incredibly difficult to detect, but Webb's infrared vision allows it to pick them out. The existence of these faint galaxies suggests that galaxy formation is a more complex process than we previously thought. This means that the universe is even more diverse and complex than we imagined. There are galaxies of all shapes and sizes, and they are constantly interacting with each other. The Webb telescope is providing us with a new perspective on the universe, and it is helping us to understand the processes that have shaped it over billions of years. What happens when Webb observes the same region of space multiple times over a period of years? This allows astronomers to track the movement of galaxies and to measure their distances more accurately. This information is crucial for understanding the expansion of the universe and the nature of dark energy. Webb is not just a tool for discovery. It is also a tool for testing our theories about the universe. By comparing Webb's observations with the predictions of our theoretical models, we can refine our understanding of the cosmos. This is a continuous process of observation, theory, and refinement. And as we learn more about the universe, we are also learning more about ourselves. We are a part of this vast and complex cosmos, and our fate is intertwined with its fate. The Webb telescope is helping us to understand our place in the universe, and it is inspiring us to explore the unknown. What could be more terrifying than realizing how much we don't know? What if everything we thought we knew about the early universe is wrong? Webb's data from the epoch of cosmic dawn, the first few 100 million years after the Big Bang, is presenting some serious challenges to our understanding of galaxy formation. It's not just a matter of tweaking existing models. The observations suggest that the fundamental processes at play might be completely different than what we've been assuming for decades. Consider the size and maturity of the galaxies Webb is seeing at these extreme distances. We expected to find small, relatively disorganized proto-galaxies, slowly coalescing from the primordial soup of hydrogen and helium. Instead, we're finding galaxies that are surprisingly massive and well-structured, with developed spiral arms and central bulges. Some even appear to host supermassive black holes, which is, well, it's unsettling to say the least. How did these galaxies form so quickly? The standard model of hierarchical structure formation, which has been the cornerstone of cosmology for years, struggles to explain this. This model suggests that small structures form first and then gradually merge to form larger ones. But Webb is showing us that large, complex structures were already in place much earlier than anticipated. It's like finding fully grown trees sprouting from the ground just weeks after a forest fire. It doesn't fit the timeline. The implications extend beyond just galaxy formation. If our understanding of the early universe is flawed, it could have ripple effects on our understanding of dark matter, dark energy, and the overall evolution of the cosmos. These are fundamental components of the universe as we understand it. If one piece shifts, the entire structure could crumble. One particularly puzzling observation is the abundance of heavy elements heavier than hydrogen and helium in these early galaxies. These elements are forged in the cores of stars and released into the universe through supernova explosions. The presence of these elements suggests that star formation was rampant in the early universe, much more so than our models predict. The data shows that not only were there stars, but there were enough of them going supernova to enrich the interstellar medium with heavy elements to the levels that we are seeing. This brings us to another conundrum, the timescale. It takes time for stars to form, evolve, and then explode as supernova. For these heavy elements to be so abundant in the early universe, star formation would have had to proceed at an incredibly rapid pace. This requires conditions that are difficult to reconcile with our current understanding of the early universe. Scientists discovered that the James Webb Space Telescope is essentially rewriting the book on galaxy evolution. The previous narrative was a slow, gradual process. Now, it seems like things happened much faster and more efficiently. This raises questions about the initial conditions of the universe and the processes that govern the formation of the first stars and galaxies. The problem is further compounded by the fact that these early galaxies appear to be more luminous than expected. This could be due to a number of factors, including higher rates of star formation, the presence of active galactic nuclei, supermassive black holes actively accreting matter, or even a different initial mass function, the distribution of stellar masses at birth. Further examination revealed that many of these distant galaxies are heavily obscured by dust. This dust absorbs much of the ultraviolet and visible light emitted by the stars, making the galaxies appear fainter than they actually are. Webb's infrared vision allows it to peer through this dust, revealing the true luminosity of these galaxies. But even after accounting for dust obscuration, these galaxies are still surprisingly bright. This means that we may be underestimating the number of stars in these early galaxies, or that the stars themselves are more massive and luminous than we thought. It's a complex puzzle with many pieces, and Webb is providing us with new data that is forcing us to rethink our assumptions. Here's what's wild. The very earliest galaxies may have been fundamentally different from the galaxies we see today. They may have been more compact, more gas-rich, and more prone to mergers. They may have also had a different mix of stellar populations, with a higher proportion of massive, short-lived stars. Measurements showed that the abundance of these massive stars would have had a significant impact on the evolution of these galaxies, influencing their luminosity, their chemical composition, and their overall structure. It's like discovering that the building blocks of the universe were assembled in a way we never imagined. All of this points to a need for new theoretical models that can explain the observations from Webb. These models will need to incorporate a more nuanced understanding of the physics of the early universe, including the effects of dark matter, dark energy, and the interplay between gas, stars, and black holes. The analysis continued. Perhaps there were unknown processes at play that accelerated galaxy formation in the early universe. Perhaps the initial conditions of the universe were different than we thought. Or perhaps our understanding of gravity itself is incomplete. Scientists discovered that it's a humbling experience to realize how much we still don't know about the universe. But it's also an exciting time to be a scientist, as Webb is providing us with new data that is pushing the boundaries of our knowledge. The implications extend to our understanding of our own place in the cosmos. The formation of the Milky Way, the galaxy we call home, was undoubtedly influenced by the processes that shaped the early universe. By studying these distant galaxies, we can gain insights into the origins of our own galaxy and the conditions that led to the emergence of life on Earth. And then there's the unsettling possibility that our fundamental assumptions about the universe are wrong. It's a terrifying prospect, but it's also a necessary one. Science progresses by questioning existing theories and seeking new explanations for unexplained phenomena. Webb's observations are forcing us to do just that. Want to join the search for the truth?